SwayamPrabha. Digital India. Educated India.
Welcome to today's lecture. We made a beginning to understand the magmatic hydrothermal system and the resulting deposit, taking the porphyry copper deposits as the example, and we would look at it a little more details, and so that the and as you have discussed, the other deposits are also somehow closely related to these deposits. And in the last lecture we saw that these porphyry copper deposits are specifically associated with felsic magmatic rocks ranging in composition from granite to granodiorite, quartz diorite, diorite, monzonite, even going up to a little more alkaline variety, syenite also rarely. If we take the entire class, the copper, molybdenum, gold, porphyries in general. Let us take a look on this figure, which is a model for the occurrence of the porphyry copper deposits. What we see here is generally what we see, that the porphyry copper deposit is associated with a small plug like body, magmatic body of felsic composition, the range which we have already seen, and this small stock is giving rise to a deposit, the quantity of the metals which we get in terms of several thousands, several hundreds of tons, even reaching to sometimes 1,000 million tons. So if we go by a mass balance, or this granite being the sole contributor of the metal, of course there is no other possible source here, it is the granite which is the source for the metal, then it does look like that such huge mineralization is very unlikely to be resulted by a small granitic body like this. With our understanding on the felsic system in general, and looking into the porphyry system in particular, this model was proposed long back, where it is proposed that what we see as a small stock in the mineralized area, whichever porphyry deposit we visit, it is actually a result of a much larger felsic magmatic system in the subcrustal level or deeper levels, and this small body is the one which actually gets separated out of the larger granitic pluton, which was emplaced at a particular depth condition in the earth's crust. And so this is a generalized model which is given for the porphyry copper deposits. We will discuss about the different alteration zones, but these deposits are essentially characterized by the alteration zones which surround the mineralized pluton, mineralized plug like body, small plug like body, and has a very characteristic porphyritic texture, from which the name of the deposit is derived as porphyry type deposit. They do have a porphyritic texture in the so having some early formed phenocryst and with groundmass saccharoidal type of texture, and they are associated with many other features, for example abrexia, and then some it's intruding into the country rock, which is by schematically shown here, and as we know them, they occur in the continental arc type of setting, Chilean Andes, where essentially they are stratovolcano type structure. Now these are some of the schematic diagram proposed based on the understanding of the felsic system and the way they evolve and the mineralization is resulted. First of all, as we know from the very source from which the granitic magma are generated, they are generated from some kind of a basaltic amphibolite type of source which contain water in their structure, and the water content could be anything like 2 to 5 wet%. And what is more important is that when the rocks partially melt, the amount of water that is contributed by the partial melt, which can be also be calculated by taking some mass balance calculations. And if we take this particular body which is emplaced in any part of the crust, then during the progress of crystallization, this represents a hypothetical 1000-degree solidus for the system. And what is shown here is there are some smaller injections of this same felsic materials in the form of dikes here, and this S1 is representing the water saturated solidus surface. The solidus is actually suppressed here because of the water content, and this particular crystallizing body with crystallization of substantial crystallization of the main with the early crystallizing phases, the residual melt is becoming charged or is concentrated with respect to water, which keeps on increasing and is accumulating on the top part, which can be called as a water saturated carpus. Now here at a later stage of solidification, this volatile water along with all the chlorine, fluorine and sulfurous vapor all are accumulating in the carpus. They are exerting pressure on the overlying rock, and if the yield strength of the overlying rock is exceeded, then this results in a network, the region which is essentially a network of fracture, and through which the crystal melt mass along with the residual fluid is emplaced within the shallow part of the system, and which is exemplified very dense network of fractures which almost are basically called as the stockwork and resulted by the hydrofracturing. The amount of pressure that is exerted with the percentage of fluid that is accumulated or exerting the pressure can be very well calculated from thermodynamic consideration by the change in volume of the fluid with decrease in pressure. And so here this also sometimes referred to as a situation which is this separation of the volatile phase from crystallizing magma with initial crystallization of the anhydrous or very nominally hydrous minerals. This is something called as a retrograde boiling or second boiling, and accumulation of the fluid within the carpus region of the crystallizing pluton and exerting pressure, which results in this region where the small plug like body is emplaced, and is also there is brecciation in the rock. So this gives us a very dense network of fracture and a complicated pattern, but this is actually the region in which the fluid deposits whatever. So whatever is so during the melt fluid equilibria, metals like copper, which essentially is incompatible during the solid melt solid melt evolution process, acts as incompatible or gets very strongly partitioned into the volatile, which gets exsolved out of this crystallizing melt. So the fluid which exsols from this melt is substantially rich in metals like copper and also gold, and they are deposited as within this region in a very well defined mineralized part, which we'll see here. So in a later stage where this hydrothermal system is waning, almost coming to the closing stage of the system, there we see there are lots of such dikes, and the brecciated regions, and so with this general picture of evolution of a magmatic hydrothermal system, which actually applies to almost all the magmatic system associated with felsic magmatism, will follow a sequence where there may be difference here and there based on what is the original or what is the initial so the critical parameter as we proposed at the very beginning, the initial water content and the value of water concentration at saturation, that means the point at which the fluid phase is getting saturated, getting separated or exsolved out of the crystallizing melt. They are the critical parameter, the ratio, the value that we get by dividing the original water content, which we can represent as a parameter which is a concentration which we call as a concentration of water of the melt initially when it is initial as Cl0 to a value of water at S. So, this is the initial concentration or initial concentration of water in terms of weight percent, and this value which could be it is like the value at a volatile saturation. So, this ratio CWL0 by CWLS is usually high if the water the original water content is high and the is low, and there has been good amount of crystallization of the melt, and then it is attaining the water saturation. It also very sensitive to the depth at which it is emplaced, and in the context of the porphyry copper deposits, they are generally emplaced at depths corresponding to pressure of almost 500 bars to 2 kilobars, not more than that. That means almost about 6-7 kilometers to 2 kilometers to 3 kilometers in the below the earth's surface. So, what results by this process can be schematically shown on this diagram. It is taken from one particular deposit in this kind of a fault which is shown as the San Manuel. This is from the San Manuel Kalamazoo deposit in Arizona, and if we look at these two diagram here, then this is the core representing the small plug like body which is emplaced, and then it is surrounding. So, surrounding that is essentially a zone where there is a low grade mineralization, this is chalcopyrite, pyrite and molybdenite, and then there is a rich ore cell part which contains the maximum concentration of copper and the richest part of the ore body, and is surrounded by again a shell where the it's pyrite rich, but chalcopyrite is poor and the mineralization dies out and that becomes a country rock. So, here this has a very good correspondence with the alteration which we will be discussing here, the core part which also is the highest temperature, and the fluid has got all the signatures of a directly magmatically derived fluid with high salinity and very high temperature, and this zone is characterized by the kind of mineral alteration which we call them as potassic, which we will see the reactions. Potassic alteration, this is the phylic alteration which is dominated by assemblage of quartz and sericite, and the ore cell is essentially or the richest part of the mineralization coincides with the boundary of the potassic and the phylic alteration zones, and then there is the argillic alteration zone, and then it is surrounded by a propylitic alteration zone, and sometimes we do also have a advanced argillic zone which we will be discussing in a short while. So, taking the taking the magmatic deposits associated with felsic rocks, the felsic magmatic system, this is kind of a generalized picture which can be obtained and is observed in deposits all over the world. There may be some minor variations here and there, sometimes all the alteration zones may not be developed, or one later alteration zone might mask or might imprint the earlier alteration zone, and many variations are possible depending on the local geological conditions, but porphyry copper deposits all over the world do conform to such kind of a general morphology. So, here since we in this particular course we will be looking at the ore deposits without getting into details into the ore genesis, we can always see them, what exactly the kind of morphology that is resulted, the associated features, that helps us in a very meaningful way. So, the hydrothermal alteration zones, so basically the hydrothermal alteration zones, we can say that in an evolving system, the fluid evolves to such a state that the fluid becomes, or the early formed mineral assemblages are out of equilibrium with the changed chemistry of the fluid. And this example is the potassic alteration in the core of the porphyry copper porphyry type deposits, where early hornblende gets altered to biotite and plagioclase to potash feldspar. Plagioclase to potash feldspar can be simply written by a very simple reaction of addition of potash to a like an albite plus potash, giving rise to potash feldspar plus soda. So, it very much controlled by the concentration ratios of these two important elements, which is sodium and potassium, or we can even write such reactions for calcium. So, this reaction, which is hypothetically this is an adenitic hornblende, which is acted upon by the potash rich fluid, which is there in the core of the evolution of the hydrothermal fluid, and this fluid is the pH of the fluid is such that we have there in the sulfate stability field. So, this reaction is proposed for conversion of hornblende to biotite in a potassic alteration zone, typically seen in the core of the porphyry copper deposit. What is to be observed here is this also gives rise to calcium sulfate, which is anhydrite, which is a very ubiquitous in occurrence in the core zone of the porphyry copper deposits very widely, and this is taken one of the important criteria for identification of or labeling a deposit or telling a deposit whether it is porphyry copper or not, when it is understood that most of the sulfur, or in the form when the fluid is in sulfate, or most of in the oxidation, in the higher oxidation state, it has also got important bearing in the sense that the metals which were initially dissolved in the melt will not be getting precipitated in the form of sulfides or disseminated sulfide. In that case, the result getting a highly enriched deposit would not be possible. So, the fluid essentially has to have a higher oxidation state at the beginning, so that the metals, most of these important metals like copper, molybdenum or gold, will get partitioned into the vapor phase efficiently, so that the deposit will result. So, this is the generally labeled the potassic alteration zone, which is at the core of the porphyry system. Then when we just saw in the diagram, where the concentric cells of the alteration zones arranged around the centralized mineralized body, we have the phylic and the argillic alteration zones, where the phylic alteration zone can be represented by reaction as potash feldspar is acted upon hydrolyzed by H plus ion to give rise to muscovite, which is essentially in the alteration zone it is sericite, the white mica plus silica and liberation of the potassium ion. So, it is understandable that it is essentially the pH of the fluid which is coming to be the controlling factor, and one of the interesting thing here is that with the warning stage, one of the important aspect of the warning stage of the magmatic hydrothermal system like porphyry copper here, now once the system is the hydrothermal or the magmatic stage is coming to a close, that time it has enough of opportunity for fluids, low temperature fluids like the meteoric fluid essentially to come to actually get infiltrated into the system and interact with the materials to give rise to different types of alterations. And the phylic, and then when we see the argillic alteration, where a mineral which is produced here in the say phylic zone is muscovite, which is getting again attacked by H plus ion to give rise to kaolinite, which is the index mineral or the mineral which exemplifies or which characterizes the argillic alteration zone around the porphyry copper deposit following or immediately enveloping the phylic alteration zone. Sometimes we do get the advanced argillic alteration giving rise to minerals like alunite, where the kaolinite which is produced in the argillic alteration zone is again acted upon by potash, and very low acidic, the pH has gone to much lower value with abundance of hydrogen ion. This gives rise to alunite, and alunite is one of the very characteristic mineral associated with the advanced argillic alteration zones in porphyry copper deposits. There are several such reactions which can be written. Muscovite can be acted upon by sulfate and at a very low pH conditions to give alunite, or even potash feldspar also at very low pH conditions can give rise to alunite. So it does explain to some extent some of the overlapping situations in which the one alteration zone can penetrate into the other, but in most of the cases the alteration zones can be identifiable, and the alteration zone which is basically labeled as a propylitic alteration zone, which is characterized by the presence of biotite and chlorite, epidote and chlorite, that is a little bit of a difference here, because it is a zone which rather indicates rock dominated or low fluid by fluid by rock ratio, and kind of the original green schist facies assemblies, persistence of the original green schist facies type assemblies in the rock. So, what essentially we are getting a system here, the porphyry copper deposits are very much characterized by multiple phases of such intrusions in one particular. If we see the sections of many such deposits, we find that there are many phases of such felsic intrusions in one particular deposit, particular mineralization zone, and sometimes it is observed that the latest phase is essentially the productive stage, which is a product of the crystallization evolution of a larger magmatic melt, granitic magmatic melt at depth. So, the alteration that we get is essentially within this granitic or the felsic country rock which are there, or sometimes could be the sediments. So, this alteration, the propylitic alteration zone, is characterized by presence of biotite and epidote, which we can see that this is a hornblende which can get altered to phlogopite as we saw before, or a phlogopite kind of biotite can be hydrolyzed to give rise to chlorite. So, maybe the combination of such kind of reactions will be giving rise to a situation where we will have epidote and chlorite to be dominant in this alteration zone, which is characteristic of the propylitic alteration zone. And it is understood that from potassic zone to the advanced argillic zone and the propylitic zone, the temperature of the fluid is decreasing. It is gradually from an original magmatic fluid which is getting cooled because with mixing of meteoritic fluid, and also in terms of the salinity, the salinity of the fluid is the higher, is the most in the potassic alteration zone, where the fluid inclusion sometimes shows presence of multiple daughter phases, and the salinity in terms of weight percent NaCl equivalent going to almost 60, 65 or 70 in many studied well studied porphyry copper deposits in the Western American Cordillera. So isotopic studies and many other kind of studies done on the porphyry copper deposits very clearly shows the involvement of magmatic fluid. So this is the general characteristic of the porphyry copper deposits around the world. Variations. So with that in mind, if we just try to see what the porphyry molybdenum deposits are, that the porphyry molybdenum deposits generally do have an antipathetic relationship with copper in terms of the distribution. The areas like the Chilean Andes or the regions in the West American Cordillera where there are dominance of porphyry copper deposit, we do not see much of molybdenum deposits there. The ones which are like the example is the Climax deposit in Colorado, or the this Henderson and Climax in Colorado, and there are some such deposits, rich deposit of molybdenum, which are not associated with or not in very close spatial association with the porphyry copper deposits. There possibly something which is critical about molybdenum deposits, or which exactly was not very well known, although many of the porphyry copper deposits do have concentrations of molybdenum in insignificant quantity. So, here the difference which have been found out in such cases is that the parent magma is more enriched with fluorine and other volatiles. So, it apparently it looks like that the source the magmatic rock which gives rise to porphyry molybdenum deposit is more felsic in its composition and have a very high concentration of the more volatile components like fluorine and other volatile species. It is indicated by presence of topaz and abundance of fluorite along with the in the alteration zones and mineralization domains in the porphyry molybdenum deposit. And one of the important differences, as was discussed here, is a critical parameter, which is the ratio of the CWL0 by CWLS, that is the original the initial water content divided by the water content at saturation is generally very high in case of molybdenum deposits and is low in case of copper deposit. Because of the very inherent difference between these two elements, molybdenum and copper, copper is more compatible than molybdenum in its nature. Although porphyry copper deposits are abundant in other parts of circum-Pacific, so this is what exactly we have been seeing, that in the circum-Pacific region, Iran, China and many other in the Chilean Andes, these porphyry molybdenum deposits are rather rare and are mostly confined to the Western American Cordillera. The rich molybdenum deposits appear to be associated with the rift phase, which is actually not very conclusively known in case of the porphyry copper deposits, that the rather poorer or lean porphyry molybdenum deposits are associated with the magmatic bodies which are product during the convergent type tectonic settings, whereas the rich part or the richest part of the porphyry molybdenum deposit are associated with a situation which more corresponds to a rifting phase, where you have highly evolved rhyolitic and alkaline kind of magma which gives rise to porphyry molybdenum deposit, which is not known in the porphyry copper deposit situation. Whereas the alteration characteristics are more or less similar in the two types of deposits. We do have the other class, the other type of porphyry deposits, which are the porphyry tin deposits. They also do, they are mostly spatially, if we look at the Chilean Andes margin, like if this is the Chilean Andes, this generally is the copper belt, porphyry copper belt, and a little to the eastern side we have this is the tin belt and the Bolivian tin deposits which are observed to be occurring to the eastern or the continental side from the Andean margin, and so more or less conforming to the similar kind of architecture. The porphyry tin deposits, the only difference is that the way we saw the stock in case of the porphyry copper deposits, which is more cylindrical and is emplaced in the form of a porphyritic stock with a small plug like body, maximum occurring within just about a 1 square kilometer or so. This porphyry tin deposit, the magmatic body is characteristically inverted cone shaped kind of body, and the potassic alteration zone is generally misses from these porphyry tin deposits, and here it is also observed that the main fundamental difference between a porphyry copper and a porphyry tin deposit is that the parent magma which gives rise to the porphyry tin deposits do have a much lower oxidation state corresponding to the porphyry copper deposit. In fact, in the context of the tin and the copper deposit, there is a classification scheme that was proposed for the granitoids, which is basically the I type, which I have already stated, which is basically the I standing for igneous protolith or igneous precursor. Compared to that, the granitoids which are named as S type, S standing for sedimentary, and these S type granites were generated little bit away. If we look at the continental, the Chilean margin, so here we have the Chilean Andes, and the melts which are generating from here, which are more, it is coming from the melting of the slab and is basically forming the stratovolcano, and that is the region for the porphyry copper deposit. The melts which are generated in these regions, if this is the Chilean Andes copper zone, then this zone actually represent the zone in which this S type magma, by melting of the already available crust, is melting to give rise to the magma which are the S type, and the S type magma are observed to be of lower oxidation state or kind of reduced, maybe because of the fact that they are derived from the sediment, the melting of the sediments which are originally containing some carbonaceous material in them. Because of that, the melt which is generated, the S type are reducing, and that is how they could carry the tin in a +2 oxidation state, and during the later stage when the fluid is mixing with fluids of higher oxidation state, the deposition is taking place. So the only thing is that even though these deposits like Bolivian tin are being labeled as porphyry type, but there are many variations in their characteristics, and sometimes there is some amount of debate as to whether they truly represent porphyry type or not. But as of the present state of the art knowledge, we do call them as the porphyry tin deposits. So thank you for today. We will be continuing this discussion in the next class. Thank you.